Okay, guys. This is our first to last day in this unit. Assuming it will, so the test will be on Friday. And so what we're going to do today is take a similarly superficial look at oxidation reduction. Now guys, the thing that's amazing is that this is also the last thing we're going to do this year. Chapter 20, Oxidation Reduction, will be our last unit of the year. So we're going to go over the fundamentals of oxidation and reduction today, similar to the way that we went over the fundamentals of acids and bases last time. The difference being, you had done acids and bases before. So you add some background, you add something to build on. Guys, we haven't done this. We did not do oxidation reduction chemistry at all last year. So this is going to be universally unfamiliar to all of you. And so we're going to go over this again very superficially. And then understand, guys, we'll come back and spend about 3.5 weeks on this at the end of the year. You good? Okay. So guys, what we're going to do is we are going to begin by defining some terms. Now guys, understand that eventually you are going to need to know these terms cold. This is the hardest part of this when we get to it in chapter 20, is remembering what oxidation and reduction mean. I'll introduce them to you today. We'll talk a little bit about where the names come from, because eventually you're going to have to know these things conversationally. So with that said, first of all, oxidation. Because oxidation refers to the loss of electrons by a substance. So you ready? This is a little more than food for thought. This is a conversation worth having because it'll help you remember and understand what oxidation really means. So guys, here's where we are. We understand that oxidation means the loss of electrons. Why on earth would chemists call the loss of electrons oxidation? Yeah. Exactly. So guys, oxidation, oxygen, right? So let's talk about oxygen. You may want to write this down with me. I don't know why it's doing that. Let's try a different pen. So guys, oxygen looks like this, right? 6 valence electrons, 2 bonding sites. What do you know about the electronegativity of oxygen? High or low? Pretty high, right? So guys, this is the deal with oxygen. It's small. It's highly electronegative, it's got places for 2 electrons, and it's abundant. It is everywhere around us. And so as Eliza pointed out, when they originally started studying these exchange of electron reactions, they found that in nature, the majority of the time a substance was losing electrons, it was losing those electrons to oxygen. Again, why? It's abundant, it's highly electronegative, and it's got space for electrons. So when they sort of began to realize that losing electrons many times happens to oxygen, they said, let's call it oxidation. You get the idea? Okay. So guys, with that as background then, the question is this. If we can't see electrons move, how do we know something's been oxidized? So you're a metal atom. Just recently have we been able to image atoms. Certainly we can't see their electrons. So guys, what do we look for to see that an atom has lost electrons? What's going to happen to that atom? Its charge changes. So if you lose electrons, what happens to your charge? It becomes positive or more positive. If it starts as negative, it could become 0, starts as -2, it could become -1. But guys, the idea is that when something is oxidized, it becomes more positive. Now, of course, the other side of this is reduction. Now, this one makes a little bit more sense. So, if oxidation is losing electrons, what is reduction? The gaining of electrons. Now, guys, again, the same thing holds true. In the same way that you can't see electrons being lost, you can't see them being gained. So, what happens to the element that is being reduced? Its charge goes down. And guess what we call going down? We call it being reduced, right? So that's actually where the name reduction comes from, because the charge of the thing that's being reduced is becoming more negative. So we can summarize it this way. The charge of the particle that's being reduced is reduced. Or, and I wonder, Josh, if you guys learned this, for some reason up at the U in the summer thing, they like to teach oil rig. Did you guys get oil rig? No? So oxidation is lost, reduction is gain. That's college level tricky. But they didn't teach that to you? Yeah, you learned about oxidation reduction, but apparently the professor that was teaching redox chemistry at the U program 2 summers ago taught everybody oil rig, and the students that I had that were there 2 years ago came back, and this was like life-changing for them. So they asked if I would please pause my slideshow, add oil rig as a bullet point, and then make sure I share that with future classes, because they thought it was that helpful. So there you go. So guys, bottom line is this. You need to remember that oxidation means losing electrons, reduction means gaining electrons, and if oil rig helps you with that, then you have last year's class to thank. But you do need to be able to keep those two straight. So guys, this then is the idea. You can't have one without the other. Think about it. In the same way you can't have an acid without a base. What? Wrap your head around that. Why can't you have an acid without a base? Because the acids lose protons, but where do they go? To the base. They've got to go somewhere. It could be water, it could be another compound. But guys, you can't have an acid without a base. In the same way, you can't have oxidation without reduction, and vice versa. The electrons have got to go from somewhere to somewhere. And so when we bring these all together, we flip the names around. When we say this as their complete names, we call them oxidation-reduction reactions, but when we shorten it, we call them redox reactions. So we can't have one without the other. So an oxidation-reduction or a redox reaction is simply a reaction where electrons are exchanged between substances. Now, yeah, go ahead. Electrons being exchanged. Here's the danger in that though, Caleb, is a lot of times what I find my students will do is when they have that aha moment and go, oh, protons are acids and electrons are redox, and they start to draw too many parallels between the two processes. You're right. The acid base is an exchange of protons, redox is an exchange of electrons, but I'd be really careful to run down that path too far, because the similarities almost stop there. So yeah. Okay, so guys, this then becomes the challenge. When redox reactions take place, what happens is the oxidation numbers change. Remember we said charges become more positive and more negative during redox processes, but remember we call those charges oxidation numbers. So guys, what we're going to do, and this, frankly, we're almost done today. This goes fast. Guys, what you need to learn to do is this. You need to learn some fundamental rules about identifying oxidation numbers. Then what we're going to do is we're going to balance some redox reactions, make sure you understand how to play the game, and then we're done for the day. So today's a fairly short day. So it goes like this. These are the rules for assigning oxidation numbers. I would encourage you to take notes and not dictations, because these get wordy, and you can just simply write down the important points. So how do we know the oxidation numbers for elements? Well, guys, rule number one is this. All atoms in their elemental form have an oxidation number of 0. So you could just write down elements equals 0. Or some of you could write down every stinking word. I really think that one of the best things that we could do for you all would be to send you to BYU for a couple weeks and just let you get the crap beat out of you by university professors, and then bring you back here. And I think, well, one, you'd like your teachers a lot more, but two, you'd also understand that there are things you got to learn to do, like take notes and not dictations. Okay, so, but some of you are still writing, so we'll wait. You got it? All right, try writing this one down. Rule number 2 is this. For monatomic ions, the oxidation number equals the charge. Rather than try to write that down, let me explain to you what I'm talking about. You ready? You guys don't have your periodic tables out, right? So everybody squint and pretend like you can see this, okay? So like, for example, if you look at magnesium, magnesium's got a bitty little 2 above it, right? What does that mean? Well, we said that those are the oxidation numbers, yeah? You okay? Guys, here's what's going on. And we talked about this a little bit last year, but we need to talk more about this now. These are not the same. In this class and in AP, they will not expect you to be able to differentiate between these two. They will actually accept either one of these as being correct. But guys, you've got, actually, you know what, let me do a different one because this one's a little bit wrong. We'll do this, aluminum, Al3+, and I'll explain to you why I exchanged them in a minute. So guys, these are not the same. So what's the difference? And I would encourage you to write this down. Guys, this is an oxidation number, and this is an ionic charge. So if you write aluminum +3, that's an oxidation number. If you write aluminum 3+, that is an ionic charge. So what's the difference? Oxidation numbers refer to sharing, which relates to covalent bonding. Ionic charges refer to loss or gain, losing or gaining, and that relates to ionic bonding. So guys, the idea is this. For example, aluminum. Aluminum can form ionic bonds, and aluminum can form covalent bonds. When aluminum forms covalent bonds, this +3 is its oxidation number, which tells you how many electrons it wants to share. When aluminum loses its electrons, it is forming an ionic charge through the loss, in this case, of electrons, and that allows it to form ionic bonds. So guys, the bottom line, and that's what this is saying, these are typically the same. Bottom line is this: the number of electrons that an atom will share also tends to be the number of electrons it will lose. That's what that second sentence is saying. But again, guys, when you get to the university level, or as they say in Europe, when you get to university, the way this happens is a lot of your professors will not allow you to use these interchangeably, because this means sharing and covalent bond, and this means losing an ionic bond, and technically they're not the same, even though the numbers tend to be the same. You okay? So technically, guys, if it's a salt, it would be this, and if it's a molecule, it would be that. Okay? So what was the one that I wrote up here first? Yeah, why did I back off on magnesium? Exactly. Magnesium is incapable of covalent bonding. It is so weak. Well, maybe not. It might covalently bond. But guys, magnesium is so weak, I can't think of instances where it does covalently bond. It just tends to ionically bond. Okay, so with all of that said, now you don't need to write down this, because that's exactly what this is talking about. Okay, so ions are represented as charge then number. Molecules and sharing are number and then charge. Or charge then sign, sign then charge. Okay, number 3. Nonmetals tend to have negative oxidation numbers. That means they take them in. Number 4. Hydrogen, when it's bonded to a nonmetal, will go positive. And when it's bonded to a metal, will go negative. The bottom line is hydrogen is right in the middle, so it'll do what the other guy wants it to. So nonmetals like to take in electrons, so hydrogen will tend to share them out. And then if hydrogen is bonded to a metal, the metal wants to give away electrons, so hydrogen will take them in. So you could just write down, hydrogen's easy to get along with. Or you could write down every stinking word. Or you could print the notes. All right, next. You're going to like this one. The sum of all the oxidation numbers in a compound is 0. What does that mean? You'll see. Compare it with this. The sum of all the oxidation numbers in a polyatomic ion is the charge of the ion. And now, guys, that your head is about to explode, we'll go through and we'll work 2 of these examples, and then we're done for the day, and you'll have a chance to work on your homework. And by the way, guys, the examples that I'm about to show you will cover all of this, and I think you'll find that this is easier than it appears at first. And some of you, from having outlined the chapter, may remember that this is just bulleted points in chapter 4. You didn't have to write down any of this. You guys okay? Can we look at examples? All right. So guys, these are the 2 types of oxidation reduction reactions that you need to be aware of right now. So what we are going to do is we are only going to talk about the oxidation of metals at this point. So what does oxidation mean? What does oxidation mean? Losing electrons. So picture what we're talking about. The oxidation of a metal. So you've got a metal atom, and when it's oxidized, what does it do? Loses electrons. And where are they going to go? Well, they can either go to an acid or, bless you, a salt. So guys, we are going to look at an example of each of these, what acids do when they oxidize metals and what salts do when they oxidize metals. So if nothing else today, you will understand why your car rusts here in Utah faster than most other western states. Right? Because what do we spread on our roads in the winter? Salts. And those salts oxidize the metal in your car, exposed metal, and cause them to oxidize, which we like to call rust. Yep? Okay, so guys, here we go. First of all, these things tend to be single displacement reactions. And the way that these work is the metal will begin in its elemental form, and it will be ionized by either an acid or a salt. And we'll look at one of each. Are you ready? Here we go. Let's do an acid first. So zinc reacting with hydrochloric acid. You may remember this from last year. You put the little piece of zinc in the test tube with the hydrochloric acid. You inverted the other test tube over the top. You collected the gas that was evolved. You stuck a burning wood splint in it and giggled. Remember? See? You went boop, and you went hit. Yeah. You remember? All right, so guys, let's balance this critter. You ready? I'm going to rewrite it so I can make it a little bigger. Zinc plus HCl, like so. So guys, single displacement reaction. Who's the zinc going to hook up with, the hydrogen or the chlorine? Chlorine, right? Because hydrogen's positive, chlorine's negative. You look up zinc on the, well, you don't even have, guys, you need to know the charge of zinc, actually. Yeah, they'd probably give it to you on the test. But zinc is +2. So our products are ZnCl2, and what is our other product in the single displacement reaction? Hydrogen, which is diatomic, so that's H2. And then to balance it, we simply need this. Groovy? Groovy. All right. So guys, that's old stuff. You've been doing that from last year. Now we need to explore this as an oxidation reduction reaction. So to do that, the first thing we need to do is we need to write in the oxidation numbers for these participants. So what is the oxidation number of zinc? Not +2. Look back up at your rules. And one of the rules that you learned is the oxidation number for an atom in its elemental form is 0. And guys, look here. Zinc is a solid. So if you have a chunk of solid zinc, it is in its elemental form, and therefore its oxidation number is 0. I don't, because I'm good at these. You might. The question was, do we need to write that? And the answer is, if you're trying to figure out whose charges are changing, I would. Yeah, but okay. So then, guys, HCl, you ready? What is the overall charge of the HCl molecule? 0. That is the first to last rule. What does it say? The charge of a compound is 0. Okay, so the charge of the compound is 0. Now we need the charges of the things that make it up. So what is the oxidation number of the charge of hydrogen? +1. And what's chlorine to make it equal? -1. So now you're asking yourself, how was I supposed to know that? Well, guys, if you look at chloride on the periodic table, how many valence electrons does it have? 7. So what does it want to do? Pick up 1, which gives it a -1 charge. Now, guys, hydrogen's got 1 valence electron. So does it want to gain 1 or lose 1? Either one. It does what the other one wants it to. So chloride has to be negative, so that will be positive. Yeah? Okay, now let's go over here. Guys, chlorine continues to be -1. If chloride is -1, what is the zinc now? +2. Guys, that's why this is ZnCl2. Now that the zinc is no longer in its elemental form, it reacts and bonds based upon its oxidation number. And if you look up zinc on the periodic table, it's +2. So this is +2, that's -1. What is the charge of hydrogen? It is now 0 because H2 is its elemental form. The diatomics, iodine, bromine, chlorine, fluorine, oxygen, nitrogen, and hydrogen, are in their elemental form when they're diatomic. Get the idea? Okay. So guys, we're getting closer. Now what we need to do is we need to get rid of our spectators. So let's look. Did zinc change? It changed all over the place because it started as a solid and it ended up what? Dissolved in water, right? Well, it's not bonded because remember, it's aqueous. Zinc chloride is water soluble, so it's aqueous. So in our products, do we have any zinc chloride? No, we've got zinc ions and chloride ions, right? So did the zinc change? You bet. Then guys, what about the hydrogen? It started did it start bonded to chlorine? No, it's aqueous, right? So you got protons and chlorides. Where did the hydrogen end up? What does this look like? It's a gas going away in bubbles. So did the hydrogen change? Yep. And then what about the chloride? Started dissolved in water, ended up dissolved in water. So what is it? It's a spectator. So guys, let's bring this down. Let's kill our spectators. And so here's what we've got. We've got Zn0 plus 2H plus yields Zn2 plus H2 0. That is our net ionic equation. You okay? All right. Now, guys, we're not quite done. We're going to do something new and nifty. Here we go. Are you okay? Yeah? Did I make a mistake? Because it's actually an ion. It actually gave away electrons to chlorine, so this would be an ionic charge, and it should be written like this. If you wrote it but it should also be 2 plus here. But if you wrote it the other way, they wouldn't mark it wrong. We did. Yes, and so, but the point is that this, again, oxidation numbers represent the electrons that it shares. The charges represent the electrons it lost. And zinc is not an electron sharer, it's an electron loser. So it should actually be written 2 plus and not plus 2. Is that okay? Okay. Okay, you guys, so here's the thing we haven't done before. You ready? What happened to zinc? And you're going to want to write this with me. Zinc went from 0 to 2 plus. So what happened to zinc? It was oxidized. This was oxidized and it lost 2 electrons. Now guys, and this is going to sort of make a mess, but let's look at the hydrogen. Hydrogen went from +1 to 0. So what happened to it? Its charge was reduced. So it was reduced. And how many electrons did it gain? Well, look. Each hydrogen gained how many electrons? 1. But how many hydrogens are there? 2, for a total of 2 electrons being captured. And guys, these numbers have got to match. The number of electrons lost has got to equal the number of electrons gained. You okay? Now guys, I know that there's a little bit of concern right now about whether you write this as +2 or 2 plus. Don't worry about it. It doesn't matter. For this class, it doesn't matter. You can write it either way. Okay? This does matter, though. You ready? I want you to write, it's not on the board, but I want you in your notes to write down the answer to this question. You ready? 2 questions. Question 1, and I need you to commit to an answer. And we're going to write this out in words. Don't write symbols, write words. So guys, you ready? What substance was oxidized? Please commit to something. This is going to cost you points on the AP test. Write down an answer. What substance is oxidized? Yes. And then guys, similarly, what substance is reduced? Commit to answers. What substance is oxidized and what substance is reduced? You ready? Here we go. What substance is oxidized? Zinc. Zinc is oxidized. I suspect you all got that right. Now guys, what substance is reduced? It's not hydrogen. It's not hydrogen chloride. Hydrogen is not reduced. Hydrogen chloride is not reduced. Hydrogen ion is reduced. And guys, that's important. Hydrogen is an atom with an electron. A proton and an electron. Hydrogen ion is just a proton. So you've got to be careful there. Guys, you can call this zinc, and that's fine. You can call it zinc atom if you want. But when it's not charged, we call it by its name, or you could add the word atom. Second. But when it's charged, it is not okay to call this hydrogen. That is not hydrogen. This is hydrogen. Guys, hydrogen is a gas that floats around in space. This is not hydrogen. This is hydrogen ion, which is a proton dissolved in water. So guys, understand it's hydrogen ion that's reduced. Yeah. That's fine. You can call those protons. Absolutely. That's fine. You guys okay? You could call them, that's a little redundant. They wouldn't mark it wrong. If you said hydrogen protons, they would be fine, but it is technically redundant. Okay. So guys, let's try one more. Try this. What about the oxidation of a metal by a salt? I chose copper sulfate, copper 2 sulfate. And by the way, just to make this easier, let's say that iron goes +2. Oops. Technically, there's no way for you to answer this question as written. Why can't you answer this question as written? You don't know if iron goes +2 or +3. Let's say +2. It'll make the math easier. So guys, if iron goes +2 and that hooks up with sulfate, we end up with FeSO4. And then our other product is copper. So let's assign some oxidation numbers. What's the oxidation number of iron? Yep, and hey guys, let's do this. I'm gonna show you a video of this in a minute. What does this look like? What is this? What is this? It's a nail, right? It's a nail. That's what nails are made of, is iron. This is a nail. It is a solid chunk of iron, okay? Now, do you remember what this might look like? Well, guys, copper 2 sulfate is this stuff. But this stuff is in water, so what's it going to look like? A pretty blue solution, okay? Now, this is where this gets a little bit tricky, because now we've got this entire substance, and this entire substance has a charge of what? 0. Now, copper is +2. How do we know that copper is +2? Because it's bonded to sulfate, and sulfate is -2. So guys, this is +2. But now we got a problem. We need to know the oxidation numbers of the sulfur and the oxygen. You ready? Here's how to do this. This is a little different. Let's go to our fixed point first. What is the charge of oxygen always? -2. Now, what then is the charge of sulfur? It's not +8. Here's why. This entire thing is -2. Sulfate is -2. So what does the oxidation number of sulfur have to be in order to make the entire thing -2? +6. So if sulfur is +6 and oxygen is -2, -2 times 4 is -8, +6 leaves an overall charge of -2. Now, let's go over to the other side. Now, iron in this case has what charge? Which one did we choose? +2. Now, you ready for a trick? Did the sulfur or did the sulfate fall apart? Now, it stayed as sulfate, right? We balanced the polyatomic intact, so these didn't change. The only time the charges of the elements in a polyatomic change is if the polyatomic reorganizes. And then, guys, what's the charge of this? 0. And what does this look like? A penny. So we magically turn nails into pennies, right? No, but you get the idea. Okay, so guys, let's kill some spectators. Who's our spectator in this reaction? Sulfate. So sulfate is gone. What happened to the iron? What happened to the iron? Was it oxidized or reduced? Iron was oxidized. It lost 2 electrons. What happened to the copper? Thank you. Nothing happened to the copper. The copper ion was reduced to what? Copper metal. So here's the way we would say that. We would say that iron metal was oxidized to iron ion, and copper ion was reduced to copper metal. Questions? You okay? So guys, let me do this for you then. I frankly wasn't planning on doing this, so I'm not really prepared for it, but I can do this quickly. I want to show you a video of what we just talked about. Electrochem. It's probably in here. Oh, it's not. Oh, this is horrible. You don't want to see that. Oh, it's here. Converting.
Copper metal deposits on this spun. Zinc electrode is immersed in a solution.
No. Hold on. That's not it. Okay, hold on. Chemistry, AP Materials, 12th edition. Whoa. You know what, guys? Let's do this. Let's be more efficient about this. Here's your homework. While you're working on your homework, I'll find the video and I'll pull you together in just a second. So guys, we're going to do 45 through 53 odd. Yeah?
So are we not doing the harder redox reactions until the end of the year then?
Yeah.
Okay.
That's right. Yeah, we'll be looking at, whoa.
So right now we just have to do this balance.
Right now, every redox reaction that we do is just going to be a simple single displacement reaction.
So will the charges always be like, or do we have to balance that?
No, you won't be doing the stuff you probably did this summer with adding hydrogens and waters, and we'll do that at the end of the year. Yeah. Okay, guys, so you fiddle with the homework while I try to find the video.